Welcome to AI Paperslop. Today we are tearing into the paper PixWorld, unifying 3D scene generation and reconstruction in pixel space. So the core insight you need to know right now is that for the longest time, 3D reconstruction and generation have been totally split. Like reconstruction used pixel regression and generation used latent diffusion.
Right.
And recent attempts to unify them in latent space, well, they suffered from massive information loss because of the autoencoders. But PixWorld just throws out the latent space entirely. It uses a unified pixel space diffusion paradigm to jointly handle both tasks in a single 1.04 billion parameter model.
Yeah, predicting pixel-aligned 3D Gaussians.
Exactly, and supervising them directly on rendered images. It beats state-of-the-art latent models in generation and matches top-tier reconstruction methods. So let's unpack how they actually pulled this off.
Well, if you're an ML engineer working in, say, embodied AI, robotics, or VR, the stakes here are incredibly high. Populating digital worlds relies on solving this exact bottleneck between two really distinct tasks.
Generation and reconstruction.
Right. You have generation on one hand, which is creating plausible environments from pure imagination or, extremely limited input. And then on the other hand, you have reconstruction, recovering highly precise geometric models from actual multi-view camera captures. Historically, tackling those required completely different architectures.
Yeah, totally different worlds.
Exactly. So unifying them means a single world model could theoretically understand both how to perfectly map a real physical room and how to seamlessly hallucinate what's behind the closed door in that exact same room using the same underlying logic.
And the major claim from the authors is that PixWorld completely ditches the latent space. But to grasp why that is such a radical shift, we kind of have to look at the current default paradigm. Like, why are latent spaces failing 3D models right now?
Well, if you examine the current mainstream approaches for 3D generation, even recent unified attempts like Gen 3R, they almost exclusively operate in compressed spaces.
Right, they rely on VAEs.
Yeah, heavily on pre-trained variational autoencoders, or the newer representation autoencoders, RAEs. The standard workflow goes basically like this. You take your high-resolution input image, you run it through the encoder to crush it down into a highly compressed latent vector.
So you can do all the heavy diffusion math in that tiny compressed space to save compute.
Exactly. And then you run it through a decoder to try and inflate it back into a 3D representation.
So it's like taking a 1,000-page, highly detailed architectural blueprint for a skyscraper, translating it into a 10-page summary document using a bunch of made-up abbreviations, that's your latent space, and then handing that summary to a construction crew and saying, all right, build a perfectly structurally sound building from this. You are inherently going to lose structural nuance.
That is a perfect analogy, yeah.
But I do have to push back a bit here. I mean, we use latent diffusion in 2D image generation every single day. The biggest image generators on the market use latent spaces to save compute, and the images look photorealistic. Why does it suddenly break down when we add a third dimension?
Because 3D reconstruction is what we call a fidelity-bound task. In 2D latent diffusion, the network can cheat. If the decoder hallucinates a slightly different brick texture on a wall or shifts a shadow by a few pixels, your brain still perceives it as a flawless image.
Right, you wouldn't even notice.
But in 3D, you are trying to establish absolute geometric truth across multiple viewpoints. When you run latent diffusion for 3D, the training objective, the loss function you use to penalize mistakes, is entirely detached from the actual 3D representation. You are grading the model based on how well it predicted the latent features, not how well it constructed the physical 3D scene.
I see. So you're grading the construction crew based on how well they memorize the 10-page summary, not on whether the skyscraper actually stays upright.
Precisely. That inherent information loss is just fatal when you require sub-millimeter geometric precision. You're basically inserting an autoencoding bottleneck between the diffusion variable and the final image space supervision. The VAE inherently discards high-frequency details to achieve that compression.
Okay, that makes sense.
So PixWorld argues that for 3D, we must keep the diffusion variable and the rendered output in the exact same RGB domain. No VAE, no autoencoding bottleneck. You process pixels and you output pixels.
Wow. That sounds incredibly compute heavy. I mean, if we abandon the latent space to preserve that geometric fidelity, how do you actually build a model that handles both tasks at the same time? Like, we need to feed it crystal clear, pristine photos of a room for reconstruction, but we also need to feed it absolute static noise for generation.
Right.
And we're asking it to make sense of both simultaneously.
Yeah, so PixWorld's input strategy handles this through a really clever partitioning mechanism. Given a set of multi-view images of a scene, the model divides them into two distinct subsets.
Okay.
You have a clean subset. These are your noise-free reconstruction anchors. And then you have a noisy subset. If you only give the model clean views and leave the noisy subset empty, the model acts as a pure 3D reconstructor. But if you populate that noisy subset, the model switches gears and generates those missing views, heavily conditioned on the clean anchor views.
Wait, but if I dump pure static and a pristine 4K photo into the exact same transformer network, my assumption is that it's just going to average the weights and blur everything into an unreadable mess. How does a single transformer process those two extremes without scrambling its own features?
They solve this with a specialized two-stream diffusion transformer, or DIT.
Two streams?
Yeah, and it's a massive architecture, 24 layers, 1.04 billion parameters. But the real breakthrough is in how the specific layers are wired. Standard transformers process everything sequentially. PixWorld uses a shared attention block, but it bifurcates the processing pathways.
So they run in parallel?
Kind of. Inside the attention operator, the tokens from the clean stream and the noise stream are concatenated together. They share a rate RMS norm.
Let me stop you there. What does a root RMS norm actually do for the streams?
So RMS norm stands for root mean square normalization. Basically, it scales the mathematical variance of the two streams, so they're speaking at the exact same volume, so to speak.
Oh, sure.
Yeah, and because they are normalized together, they can crosstalk. The noisy tokens can actively look at the clean tokens during the attention phase to pull contextual clues about what they're actually supposed to be generating.
Okay, so they're in the same room, talking to each other, sharing context. But how do you stop the static from corrupting the clean data?
That is where the separation happens. While they share attention, the network maintains completely independent pre-layer norms, independent QKV projections, and most importantly, independent SWIGLU MLPs for the clean and noise streams.
So let me see if I'm tracking this. The MLPs, the multi-layer perceptrons, those are basically the heavy calculation engines of the transformer block, right?
Exactly.
So by keeping those separate, the network can run massive denoising math on the static tokens using one engine, while running much lighter preservation math on the clean tokens with the other engine.
Yes, exactly.
And the two computations just never overwrite each other.
That is the exact mechanism. They share a global understanding of the context through the shared attention, but they execute their specific computational tasks in total isolation. And to ground all of this in physical space, the camera parameters are injected into both streams via pre-row PE.
Which poses relative positional encoding, right?
Right. And if you want to steer the generation with a text prompt, that gets fused in later through a shared cross-attention layer.
Okay, so the transformer has processed these cross-talking, clean and noisy streams. It kept the math separate. But at the end of the day, the transformer is really just pushing a massive sequence of 2D tokens around. How does it cross the bridge from 2D pixel space tokens into an actual physical 3D world?
It comes down to the multitask output heads. Earlier 3D generation methods would try to regress 3D center coordinates directly from the neural network, like trying to make the transformer spit out XYZ coordinates.
Which feels super clunky.
Very. PixWorld takes a much more elegant route. For every single pixel in those process feature maps, the model predicts two localized things, a depth map and the specific attributes for 3D Gaussian splatting.
Now, for the listener who might not be deep into rendering techniques, what exactly is 3D Gaussian splatting in this context?
Well, instead of building a world out of rigid polygons or triangles like a typical video game, Gaussian splatting builds the world out of millions of tiny mathematical blobs, ellipsoids. For every pixel, the model predicts the attributes of that blob, so its opacity, its color, and its scale or rotation.
So the model is looking at a specific 2D pixel, say a pixel showing the edge of a coffee table, and it says, I know you are a brown pixel, and based on my calculations, you exist exactly 1.2 meters away from the camera lens.
Yes. And because the network was fed the exact camera parameters earlier via PRPU-E, it knows the exact focal length and position of the lens. So it can take that 2D pixel, take the predicted 1.2 meter depth, and use a mathematical inverse projection function to literally shoot that pixel out into a 3D coordinate space. When you aggregate all those unprojected pixels across all the views, you suddenly have this dense, unified cloud of 3D Gaussians that perfectly represents the scene.
And here is where the pixel space supervision comes in. Because they threw out the latent space entirely, they take that newly generated 3D Gaussian cloud and they render it back into flat 2D images from those original camera angles.
Exactly.
It's like building a complex Lego set taking a Polaroid of it from 3 different angles, and then directly comparing your Polaroids to the reference photos on the box. Everything stays purely in the visual domain.
And that direct visual comparison is what drives the learning process, and it's powered by the flow matching loss. Flow matching is an advanced alternative to standard diffusion objectives. Instead of just predicting the noise, it predicts the velocity.
The trajectory.
Right, the optimal mathematical trajectory from pure static all the way to the clean data distribution. And because PixWorld operates entirely in pixel space, this flow matching objective is calculated directly on the rendered images. The network looks at the pixels it generated, compares them to the pixels it was supposed to generate, and updates its weights.
That makes total sense for the noisy generated views. But what about the clean anchor views, the ones that were already perfect?
The clean views act as your rigid ground truth anchors. The rendered images from the clean views are supervised with a direct mean-squared error against the original input photos. If the network alters those known views by even a fraction of a pixel, it gets heavily penalized.
That sounds foolproof on paper, but I see a massive loophole here. Rendering images and checking the pixels is elegant, but, pixels can easily lie about depth.
Oh, definitely.
Right. If the loss function is only penalizing the model based on the final 2D rendered image, couldn't the model just take the path of least resistance? Like it could generate a completely flat, floating billboard of a coffee table that looks flawless from the training camera's specific angle, but has absolutely zero 3D volume.
You've just identified the fundamental flaw of relying solely on photometric loss. If you only use 2D pixel comparisons, the network will absolutely cheat. It will create translucent floaters in the air, the depth predictions will drift along the viewing ray. It basically relies on view-dependent textures to paint over terrible underlying geometry.
Because from the exact perspective of the training camera, the math checks out.
The pixels match perfectly, but if you move the virtual camera 1 inch to the left, the illusion shatters, the table warps, and just tears apart.
So how does PixWorld force the network to actually build solid, volumetric geometry instead of cardboard cutouts?
They introduce a structural critic into the training loop. It's a frozen 3D foundation model known as Pi3.
Okay, how does a 3D foundation model differ from a standard 2D image classifier like, say, CLIP?
Well, a standard 2D critic looks at a single image and evaluates its semantic appearance, like, does this look like a coffee table? But the Pi3 model was explicitly trained on massive amounts of 3D structural data. It doesn't just look at one image.
It looks at all of them.
Right. It processes all the multi-view rendered images together alongside their camera poses. By doing that, it extracts geometry-aware feature maps. It inherently understands cross-view 3D structure.
So it's actively checking if the coffee table occupies volumetric space, rather than just checking if it's the right shade of brown.
Precisely. PixWorld takes the images it just rendered and the ground truth images and runs both sets through this frozen Pi3 critic. Then it calculates the cosine distance between their geometric feature maps and minimizes it. This geometry perception loss strictly forces the generated model to share the exact same underlying physical geometry as the real world.
If we were to turn that geometry loss off entirely, how badly would the model degrade? Do we have data on that?
We do, thanks to the ablation studies in the paper. If you disable the geometry perception loss, the entire physical consistency of the model destabilizes. Visually, the peak signal-to-noise ratio drops by 1.13 decibels, which is a very noticeable degradation in image quality. Right. But the real casualty is the camera control accuracy, which is measured by a specific metric called AUC at 5. When they drop the geometry loss, that metric plummets by 12.5%.
Can you break down what AUC at 5 is actually measuring for the listener?
Sure. AUC at 5 stands for area under the curve at a 5-degree error threshold. In simple terms, it measures how accurately the generated 3D scene aligns with the intended camera trajectory.
Oh, so if I tell the camera to move forward 1 meter and pan 30 degrees, does the generated physical space shift and behave exactly the way optics and physics dictate it should?
Exactly. And a 12.5% drop means the model fundamentally loses its grasp on physical space. It reverts right back to generating high-resolution cardboard cutouts.
So to summarize the architecture here, we have a theoretically sound pixel space model. We've got a 2-stream transformer keeping the noise math and clean math isolated. And we have a 3D structural critic acting as a geometric guardrail to stop the network from cheating physics. Let's talk about execution. For the engineers listening who actually build these pipelines, what did the training recipe look like, and what kind of data is required to teach a 1.04 billion parameter model how physics works?
The training regime is a massive undertaking. I mean, they trained this 1.04 billion parameter model entirely from scratch. There was no pre-training on existing video models to give it a head start. They utilized 32 NVIDIA A800 GPUs and trained for approximately 200,000 steps.
That is a staggering compute budget. What datasets do you even use to feed a beast like that?
The core structural data came from two heavily utilized datasets, Real Estate 10K and DL3 DV10K. That provided them with roughly 67,000 highly precise posed multi-view scenes. But the most crucial part of the recipe was actually mixing in a single image branch. They injected 10 million single flat images from the BLIVE 3.0 corpus into the training loop.
Wait, if the entire goal of this deep dive is to build a unified 3D world model, why would you dilute the training data with 10 million flat 2D images?
To aggressively strengthen the 2D appearance prior, those flat images share the exact same diffusion backbone as the 3D data. By teaching the network what a massive variety of objects, lighting conditions, and textures look like in 2D, you basically offload that learning burden.
Oh, I see.
Yeah, you free up the computational capacity of the multi-view dataset, allowing it to focus exclusively on teaching the network about complex 3D structure and geometric relationships.
Oh, that is incredibly efficient. You don't want your expensive, hard-to-acquire 3D dataset wasting its time teaching the model what a couch looks like.
Yeah.
You want it teaching the model how a couch physically obstructs light and exists in 3 dimensions.
Exactly.
So, the ultimate question, does this unified pixel space approach actually beat the heavily optimized latent models on the leaderboards?
It absolutely does. Let's look at pure reconstruction, first giving the model clean multi-view inputs and asking it to map the scene. PixWorld outperforms state-of-the-art models that are dedicated solely to reconstruction.
Really?
Yeah. For instance, when benchmarked against the pose-conditioned Splat model on the 4-view Real Estate 10K dataset, PixWorld scores an LPIPS of 0.138 compared to Splat's 0.143.
Where lower is better for LPIPS, right?
Right, meaning PixWorld is generating sharper, much more perceptually accurate reconstructions than a model custom-built for that exact task.
Beating a dedicated feed-forward reconstruction model with a unified generative model is wild. But reconstruction is the easy part. Generation hallucinating the missing halves of rooms is where models usually break. How does PixWorld hold up?
This is exactly where ditching the latent space pays its biggest dividends. They heavily tested the model on extrapolation. That is, when you give the model clean anchor views at one extreme end of a room and then command the camera to move far outside that span, creating massive camera parallax.
Can you define how Parallax specifically stresses these models?
Sure. Parallax is the optical effect, where objects closer to the camera appear to move faster across your field of view than objects in the background, like looking out a train window.
Right.
It is the ultimate stress test for 3D generation. If your geometry isn't perfect, the moment you introduce parallax, the fake 3D instantly breaks. Textures stretch, walls warp, and depth layers bleed into each other.
Total immersion breaker.
Exactly. Baselines operating in latent space, like LVSM, Gen3R, and FlashWorld, they consistently fall apart under heavy parallax. Their depth of maps become incredibly blurry because the autoencoder lost the high-frequency detail. But PixWorld dominates these extrapolation benchmarks.
Because it operates in pixels.
Yes, because it predicts per pixel depth natively, supervised directly by that 3D foundation model. It maintains razor-sharp depth maps and absolute geometric coherence, even when it is hallucinating entirely new architecture on the fly.
So, bringing this all together for you, the listener, this deep dive into PixWorld proves a monumental point for the future of spatial computing. By keeping your diffusion calculations strictly in pixel space and completely bypassing the latent autoencoder bottleneck, you achieve superior visual fidelity, dramatically better extrapolation under extreme parallax, and unmatched geometric consistency.
Yeah, you simply have to be clever about how you route the clean and noisy data through your transformer layers. And you absolutely must employ a 3D critic to keep the physics honest.
It really is a masterclass in architectural design.
It really is. But if we take a step back and look at the broader implications for the tech industry, this leaves us with a truly provocative thought.
Let's hear it.
Think about traditional rendering pipelines today. If you want to build an interactive virtual world or a video game, you rely on massive game engines like Unreal Engine. You need rigid polygon meshes, manual lighting calculations, physics simulations.
Tons of manual asset creation.
Exactly. But PixWorld just proved that a single diffusion model, operating purely in pixel space, can inherently understand geometry, volumetric depth, and camera physics perfectly on its own. It begs the question, are we looking at a future where we bypass game engines entirely? Will the video games and VR environments of the next decade simply be real-time inference runs of a massive pixel space diffusion model, hallucinating every frame of reality around you as you move?
Wow, that is a staggering implication. Why spend years manually modeling a virtual city polygon by polygon when you can just feed a pixel space diffusion model some anchor photos and let it hallucinate the physical reality in real time? Definitely something for you to chew on as you look at the future of rendering. That's all we have for today. See you next time on AI Paper Slab.